Hello students. Today we are going to discuss conservative force versus non-conservative force. Student, have you seen the skater board rolling on the ramp? What is the principle behind it? Similarly, have you seen the wobbling head of the doll? What is the force which is help this wobbling of the head of the doll continuously? Similarly, in the speedometer of your vehicle, what make the pointer to back to its original position when your vehicle is stopped? So let's understand why this happened and what are the forces responsible for this. For that, we need to know the conservative force and non-conservative force. Let's see what are the examples of the conservative force and non-conservative force. Gravitational force, spring force, and the electrostatic force is a study under conservative force. Under non-conservative force, we study frictional force, air drag, viscous force, etc. Now, let's understand what is the conservative force and the non-conservative force in the detail. Students, here you can see a ball is rolling down under the influence of the Earth's gravity over the ramp of same slope without friction. As you can see, student, this situation is the same as that of skateboard rolling on the ramp. So instead of a skateboard, we are consider ball over here. As you can see, student, this ball is rolling on the ramp of a same slope, but the ramp has no friction. Hence, its initial height and the final height where it reach is same. This happened in a case of a conservative force, as the gravitational force is the conservative force. Now let's see what happened in the case of a non-conservative force. For that, we again consider the same ramp, same ball, but here we consider the surface is not a frictionless. So here you observe, student, the ball can't reach to its original height because of the friction force, as the friction force is a non-conservative force. The name itself suggests, student, the conservative means which conserve the energy, which conserve the things. And in case of a non-conservative means it can't able to conserve the energy. Now let's understand it more detail. Now let's consider first the conservative force acts on the ball. Here is the initial height of the ball, which is h. And second, where it reach, that final height is also h. So both these height are same. This dotted line show you that the ball is reached at the same height. Initially, the ball is at position A. Here there is no motion of the ball, hence only energy possessed by the ball is the potential energy. So the total energy of the ball is the potential energy due to its height. Now let's see what are the forces acts at a point A. The gravitational force, which is act vertically downward direction. Now let's resolve this force. We have resolving force like this. Now see the diagram of a ramp. You observe the angle of inclination is a theta. Here the angle of inclination is also theta. As we already say, student, both these ramps having the same slope. Hence the theta is the angle of inclination on both sides. Here is the angle as a 90 degree. Hence the angle between the height and the inclination is 90 minus theta. As you can observe in the diagram, vector mg, that is the weight of the ball, is a parallel to the height, and the component of the weight, which is in the direction of a displacement, is a parallel to the inclination. Hence here you have angle same as that of a 90 minus theta. Hence this component is mg sin theta and this one is the mg cos theta. Now let's find the work done by the ball to move from position A to position B. We know student work done is equal to force into displacement. Here we have a W, which is the work done by the ball to move from position A to B is equal to mg sine theta into S, where S is the displacement. Note down here student, I just consider the component mg sine theta to find the work. Here the reason is that the component mg cos theta is a perpendicular to the direction of a displacement. Hence, the displacement is a perpendicular to the force. In that case, work done is zero. So only component responsible for the motion of the ball from position A to B is mg sine theta. Now, with the geometry, we can write mg sine theta into h by sine theta. So for the displacement, I substitute h upon sine theta. Sine theta get cancelled. I ultimately have work done is equal to mgh. We know student mgh is the potential energy. So the work done by the ball to move from position A to B is equal to minus change in potential energy. Negative sign indicate that there is a decrease of a potential energy. While moving from position A to B, it observed that the potential energy get converted into kinetic energy. When the ball is reached at position B, the total energy becomes the kinetic energy. It has no potential energy because the total potential energy get converted into kinetic energy. Now let's see what are the forces act on the ball when it is at position B. Mg acts vertically downward and the normal reaction at vertically down upward. So the net force acts on the ball is zero. That is, the ball is in equilibrium. So as the ball is in equilibrium, still it moves from position B to position C. How it can be possible? When the ball is moving from position A to B, it gains kinetic energy. That kinetic energy provides the inertial force which able or which make this ball to move from position B to position C. So when the ball is moves from position B to position C, the kinetic energy again get converted into potential energy. So once the ball reach at position C, its total energy again becomes the potential energy, which is same as that of position A. Now the work done for moving the ball from position B to position C is equal to change in kinetic energy. So I already told you student, only the kinetic energy is responsible for the ball to move from position B to position C. So here the work done is equal to minus of kinetic energy, or work done is a change in kinetic energy. Again, the negative sign indicate that there is a decrease of kinetic energy from position B to C, as it has to do work against the gravitational force. Now, during this motion, the work done is negative and the potential energy is positive, because during the motion potential energy increases, but as the work is done against the gravitational force, it has a negative sign. So from this discussion, we understand student, when the motion is under the gravitational force, the mechanical energy, that is the kinetic energy plus potential energy, is conserved. It is because there is no loss of energy or no any dissipation of energy during its motion. And one more thing you observe over student, the work done by the object get stored in the form of a potential energy. This can be possible only in the case of a conservative force. Now let's discuss the similarly for the non-conservative force. Now here the situation is the same ramp I am consider over here, the same ball I am consider. Only thing is that here the surface of the ramp having a friction. Now initially the ball is at height, as you can see over here, h. Next, here is the position of the ball. Total energy of the ball is a potential energy. Again, I repeat, there is no motion, hence the kinetic energy is zero, but it is at a certain height from the surface, hence it has a potential energy. Now, the ball is rolled from position A to B. So, during this motion, the friction force acts on the ball, which is in the opposite direction of a displacement. So student, work done by the ball. So student, work done while moving the ball from position A to position B is equal to minus Fs. Here negative sign indicate that student, the force and displacement both are in opposite direction. Now during this motion from position A to B, it observed that the total potential energy is not get converted into kinetic energy. So that I mention is over here, change in potential energy PE dash get convert into kinetic energy. So the some part of the potential energy get converted into kinetic energy, because the part of the or small part of the energy needs to be used to overcome or dissipate against the frictional force. So here the total energy which is you have at the position B is less as compared to the kinetic energy, because the total potential energy is not get converted into the kinetic energy. So because when the ball moves from position B to position C, which is the final position of the ball, you observe that the height is different from the initial height, and the change in the and during this motion from B to C, the total kinetic energy again is not converted into the potential energy. So I write it over here, kinetic energy is not completely converted into potential energy, so that I write PE double dash. It has happened again because student, when the ball is moved from position B to C, it again has some friction. It has to work against the friction, so the some part of a kinetic energy is used to overcome the frictional force, so that it is not possible for this ball to reach the same height. So the total energy at this position is also very small, because the potential energy is decreased. From this you can see student, in the case of a non-conservative force, mechanical energy does not conserve. So that here student, when the work done by the non-conservative force is not equal to potential energy, because the non-conservative force not able because the work done by the non-conservative force is not able to store the energy. So in that case, the work done is equal to change in the kinetic energy. Now let's see few more characteristic of a non-conservative and conservative force. In a conservative force, now let's see the ball is rolling on the frictionless ramp of a different slope, still the ball would roll up the opposite slope to its original height. Here you can see student, the ball reached to its original height. It is possible in a case of a conservative force. So here you can observe student, here you have a different slope, that is the angle of inclination, and the ball covers different distance over the two different ramp. Here you can see in the other ramp, the greater distance is covered by the ball. Still, it reached to the same height. From this, you can say that work done by the conservative force is independent of a path taken, or work done by conservative force is independent of angle of inclination. It is happened because student, the conservative force is able to store the total energy. There is no loss of energy during its motion. Now same for the non-conservative force. Now here the ball is rolling on the frictional ramp of a different slope. The situation is same, but you observe student, the ball can't reach to the same height. From this, you can see student, for the greater distance, more energy dissipate to overcome the friction force. So that as the more distance is covered, more is friction it has to be faced, and more energy is dissipate to overcome that friction. From this, I can write work done by non-conservative force is depend on the path taken, or work done by non-conservative force is depend on angle of inclination. Next, see it over here. What you observe student? The ball is moved from initial height to the final height. Again, I move the ball from the initial final height to the initial height. So this path is considered as a closed path of the motion. For the closed path of a motion, you observe the displacement of the ball is zero. That is, the initial position and the final position of the motion of the ball is same. Hence, its displacement is zero. From this, we can say, student, in the conservative force, work done over closed loop is zero. Work done depend upon the initial and the final position in the case of a conservative force. But now the same situation let's discuss for the non-conservative force. Here the ball is moved from initial height to the final height. But when it tries to reach to its original height, again it won't reach because its energy is not sufficient to reach the initial height because the energy is get dissipate against the frictional force. So that from this we can say work done over closed loop is not zero, or otherwise this object not able to reach its original height, hence its initial and the final position is not same. So that we can write the conclusion work done over closed loop is not zero in a case of a non-conservative force. Let's summarize the difference here. In a conservative force, mechanical energy is conserved. In a non-conservative force, mechanical energy is not conserved. In a conservative force, work done gets stored in the form of a potential energy. And in a case of a non-conservative force, work done is equal to change in the kinetic energy. In the case of a conservative force, work done by the conservative force is independent of a part taken, or work done by conservative force is independent of an angle of inclination. But in the case of a non-conservative force, work done by the non-conservative force is depend on the part taken, or work done by non-conservative force is depends on the angle of inclination. Work done over the closed loop is zero in the case of a conservative force. Work done over closed loop is not zero in the case of a non-conservative force. So students, with the help of a knowledge of a conservative force, we can explain the principle behind scatterboard rolling on the ramp. Here, the gravitational force is conservative force, which is responsible for the scatterboard rolling on the ramp. Similarly, in the wobble head of the doll, a spring is fixed. So the spring force is responsible for the wobbling head of the doll. Hope you understand the concept. Student, to like, share and subscribe my channel.